We've been talking through some FRQs in preparation for the AP Physics C Mechanics test. And one thing to note for 2020, because the structure of the class is different and because of coronavirus, the College Board has gone ahead and given this specific problem as an example of a longer style FRQ that could be done and should be looked at. And so we're going to be looking at it here. It's more conceptual than most FRQs. There's essentially no numbers or calculations with this. It's a different style problem and definitely worth looking at and paying close attention to. So we're going to go ahead and do that. I just got this directly from the College Board's website. It's all public information. So let's go ahead and take a look at the problem. So essentially you have a rod right here that's motionless to begin with, a disc that's moving, and it's going to have a collision here. And if you want to read more about the problem, go for it. Part A says, suppose the rod is much more massive than the disc. So this is much more massive than this, all right? To give the rod as much angular speed as possible, should the student make the disc hit the rod to the left of point C, at point C, or to the right of point C? Well, if you're familiar with torque, the idea of torque, which I've talked about previously and you've probably heard from your teacher in your class, torque is going to be greater the farther away it is from the axis of rotation over here. That's why door handles are put to the outside of a door, not towards the inside, because with the same force it would be a lot easier to open this door with a handle on the outside than with the handle, say, right here. Wouldn't really make sense to put a door handle very close to the hinge. So this part A is actually pretty easy. You're going to want to pick to the right of C. So it's just, if you understand the principle of torque, the farther away the force is from the axis of rotation, the greater the torque is going to be. And so for B, it says, on the internet, a student finds the following equation for the post-collision angular speed of the rod. This situation, omega is equal to m disc x v naught over I. Regardless of whether this equation for angular speed, does it agree with your qualitative reasoning in part A? Alright, so let's remind ourselves of what we were talking about in part A. In part A, we were talking about the torque would be greater the farther away the force is from the axis of rotation. So in light of that, we're going to focus on x. We could focus on other variables, but we're going to focus on x and ask ourselves, does it make sense to have x be proportional to omega? And so if you said, well, if the x was greater, then the angular speed would be proportionally greater as well. Does that make sense? And the answer is yes. Yes, it does. So you would explain that. You would say x should be proportional to omega right here. And it makes sense to say that's the case because the greater the distance between where the force is applied and the axis of rotation, the greater the torque is going to be. Okay, and there are a couple things that are going on with this part C. So if we take a look at it, it says another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with this. Without deriving the correct equation, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. Briefly explain your reasoning. Let's think about this here for a moment. So there are really three things we can address. But before we do anything else, I do want to be careful with what these variables mean because there's no subscript here and there's no subscript here. So are we talking about the moment of inertia for the rod or the disc here? And is this the moment of inertia of the rod or the disc? This is going to be for the rod. This is going to be for the rod as well. All right. Now I would note it's not terribly clear that what this I is. I think that makes this problem a little tough to work at. So let's first start with mass and think about what's going on with mass. Does it make sense to have mass in the denominator? Let's think about it. Well, if you had a much greater mass, then what that would mean is that your omega of the rod after the collision goes down because as you have a greater number in the denominator, the overall result of the fraction is going to be lesser. Does that make sense? The answer is no, it doesn't. If you think about if this was very massive, like a much bigger disk, and it collided with this, we would expect to have a greater angular momentum change in the rod as a result. So I would argue from that point, that's the easiest way to get the point here, is to argue that having the mass in the denominator does not make sense. A couple other points here. This is going to be the moment of inertia of the rod. So let's think about this. So if our moment of inertia goes up, the moment of inertia of the rod goes up, that would mean that the angular speed goes up with the rod after the collision. And that's the exact opposite of what we would expect. And so the moment of inertia of the rod should be down here. In my opinion, though, it's actually harder to tell what's going on with the moment of inertia. So you can prove this either way, working with mass or working with moment of inertia. I think they're equally easy to do so. It's just a little unclear in my mind of specifically what type of moment of inertia they mean with this I value here. Lastly, I find this a little distracting over here, this d to the fourth. I find it distracting because all of our moment of inertia equations that we've worked with in the past for simple shapes have been some variant of m times x or d to the second power. So that is a red flag in my mind, and I think it's a red herring. I think it's a distractor there. But in any case, you can get your point just by justifying this using mass. You don't have to worry about I or D. Alright, and for parts D and E, we now do not assume that the rod is much more massive than the disk. Alright, fair enough. That did not play into our calculation a huge amount before, but it's something to note now. So D, immediately before colliding with the rod, the disk rotational inertia about the pivot is m disk x squared. Alright, so they're giving us our moment of inertia for the disk, and its angular momentum with respect to the pivot is given to us as well. So these are a couple statements that we need to write out to make life easier for us. So we'll take a moment to write that out, and let's look at the question. It says derive an equation for the post-collision angular speed omega of the rod. Express your answer in terms of d, m disk, I, x, v naught, and physical constants as appropriate. So it is really important to get our final answer in these terms right here and to make sure we're labeling everything correctly. And if you don't do that, you don't actually get the point, believe it or not. So just be very careful to label everything exactly as they want it to be labeled at the end of it. It's a good thing to double check at the end of your problem to make sure you're doing it correctly. Alright, and so I'm just going to write down the two things they told us in here. So they're telling us the moment of inertia for the disk is this, and the angular momentum of the disk is this as well. Alright, so let's think about this. This is going to be a conservation of angular momentum problem, right? So we can go ahead and say the total angular momentum initial is equal to the total angular momentum final. Believe it or not, you can get a point for that. And it is valid to give a point for that because this is the foundation for how we solve the problem. If a student understands that, yep, momentum is conserved, so what that means is the total momentum we have before the event is equal to the total amount of momentum we have after the event, and writes that down, it's simple and profound, but important to write the stuff down. Alright, so we go ahead and we can flesh that out a little bit. We're talking about just the momentum of the disk initially, and that's because the rod is not moving, it's not rotating with any axis that we know of. It's just basically stationary, so we can ignore the momentum of the rod beforehand. So we just have the momentum of the disk initially, and we have the momentum of the disk plus the rod finally, because they move together as a combined object. I am essentially going to set all three of these things equal to each other and say, well, I know what the momentum of the disk is, and that was my initial momentum. I can work with that. And so I go ahead and just plug in what they told me was true for the momentum of the disk. And then I'm going to look at my equation sheet right here. And so on my equation sheet, I have I times omega final. I should actually get rid of that final towards the end of my problem, but for now I've left it in. The point here that you get is for demonstrating the understanding that you know when these things collide, they're going to be moving as one object, and they have one moment of inertia. It's a rotational analogy to saying that if someone catches a football, let's say, in linear momentum terms, that's an inelastic collision, and then that person who catches the football and the football are treated as if they have one mass. And that's the rotational equivalent right here. They have one moment of inertia for both objects because they've joined together. Then we say this is equal to 1 point to know our angular momentum initial is equal to the momentum of the disk, and for subbing in the equation that they gave us for that. And then over here, again, we know what the moment of inertia is for the disk, and we're going to put this in terms of the moment of inertia of the rod. We need to be careful to put this as an I, not as I sub rod, and that's because they want it in terms of their variables that they've given us here. I'm labeling this equation as 1, so when I go to the next slide you understand what I mean. And so here is our work previously. We just isolate from our unknown and we end up with this. That's one more point over here. Alright, and then part E says, consider the collision for which your equation in part D was derived, except now suppose the disk bounces backward off of the rod instead of sticking to the rod. Is the post-collision angular speed of the rod when the disk bounces off it greater than, less than, or equal to the post-collision angular speed of the rod when the disk sticks to it. All right, so if you think about it, you can have two collisions, two examples. One example, this thing collides and sticks, and another example is when this thing bounces backwards. The change in momentum for the disk is going to be greater if it bounces backwards. And so because of that, because it's bouncing backwards and it's going to have a greater change in momentum, because of that, it's going to provide a greater rotation to the object than it would have otherwise. In other words, you're going to have a greater change in momentum if the disk bounces off the rod than if it sticks to the rod, because it has a greater impulse or change in its own momentum. That means it's providing a greater impulse or change in momentum on the other object. And so if you can explain that with words, you get those 2 points. Hopefully this has been helpful. I do want to point out one thing before we leave this problem, a couple things actually. First off, I'll do more examples so you can take a look at some other things that we've done in preparation for the AP Physics test. Secondly, how were those calculations? Oh wait, there were none. Isn't that crazy? We're doing an AP Physics test and there are no calculations. I want to point this out. This is why the College Board is suggesting this is a good model for how the 2020 test is going to run, because essentially, notice there are no numbers, no calculations here, and you can still do an AP level physics problem set without using numbers, without drawing graph points. I will expect you would have to work with graphs, something along those lines, but notice you can do an entire FRQ without any calculations and without any numbers. And that's more of what you might expect for the 2020 test. There may be some numbers. You may have to read graphs and interpret data and so on and do some calculations, but they've already said that the calculations are going to be much less than a typical year in terms of the math, because they want you to be able to type these things into a prompt and be totally fine doing that. And this is an example of something where you could do that easily. In any case, I hope this has been helpful, and if you'd like to listen to some more screencasts I've done as we get ready for our test, please do so.